I'd like to welcome everyone. My name is Asaf, and I'm a Senior Director of DevOps at Opsfleet. We are a DevOps consultancy providing startups and scale-ups with managed DevOps services. Today we have partnered with PerfectScale, which provide a product that helps you ensure peak test performance at the lowest possible cost. We have two speakers with us today. First off, our very own star DevOps engineer, David Konak, will be talking and showing the different aspects of autoscaling Kubernetes. After David, PerfectScale CTO, Eli Birger, will take us through the introduction of PerfectScale and will do a demonstration for us. Feel free to submit your questions in the Q&A tab in Zoom, and we'll address those questions at the end of the talk. So passing the mic to you, David, good luck.
Thank you, Asaf, I appreciate it. Welcome everyone to this talk where with my co-host Eli, we're going to take you on a deep dive of scaling Kubernetes. It's lovely to see so many participants here, so let's get started. Before we start, I'd like to clarify that I am assuming some basic Kubernetes knowledge about such things like deployments, nodes, resources, and requirements so that we don't get lost along the way. So first, let's talk, why do we want to scale? As you start onboarding your customers to your system, there's going to be an increased load, and we want to ensure that you have a great uptime and a good user experience. Now, the typical startup lifecycle has 3 days, and scaling is needed when we get to day 2. Your first day will normally be your requirements, your architecture, your design, understanding how your application is going to look. Day 1 is setting up your application, installing your infrastructure and your applications. And then day 2, you're onboarding your customers. You need to keep the lights on, you need to do your maintenance, and most importantly, optimization. We need to get our system running in the best possible way. And this leads us to the aim of this talk, which is the best possible experience at the lowest possible price. Now, it's important to note that scaling is not a set and forget task. It requires continuous monitoring and optimization to reap the full benefits. You can't just set it and leave it. You have to continuously check, is it working? How's it working? What can we tweak? So on and so forth. So now we understand why we want to scale. Let's see actually how we do it technically. So the first thing we're going to talk about is pod autoscaling. There's 2 ways that we can scale pods, vertically and horizontally, and each has its benefits and disadvantages. Let's talk about vertical scaling first. This means that we add more resources to your pod when needed. So we have a pod, it's got some sort of resources, and as it needs more resources, we add more resources, for example, RAM and CPU to this pod. A very useful feature of vertical scaling is the VPA recommender, because what it will do is it will actually look at the historical and current usage of your pod, and it will recommend the resource requirements for your pod based on the trends. A downside of the VPA is that we need to restart the pod in order for the changes to take effect. So once it's given a recommendation and we want to add or we want to scale up, we have to restart our pod in order for those changes to take effect. And this can have a negative impact on performance and uptime. And we can only increase so much, after which adding resources becomes ineffective, leading to diminishing returns for the additional costs. You can keep adding more RAM, more CPU, you'll keep paying more for it, but after a while, you're not going to get any added benefit for this money that you pay. Now let's take a look at horizontal scaling. So this refers to adding multiple instances of the same pod and sharing the load between them. This is very useful for scaling stateless applications such as REST APIs or queue consumers. There's much more flexibility and fault tolerance, because if a node or a pod has an issue, customers will not be affected and SLAs will not be breached, because let's say we have 5 pods running. If one goes down, we still have 4 that can carry that load. You can also scale as much as you want, obviously based on cost and cloud compute capacity, but you can scale out as much as you want. But one of the downsides with horizontal scaling is it's much more difficult to use for stateful applications such as databases, because they tend to not scale well horizontally. So based on this overview of how pod autoscaling works, we're going to focus on horizontal scaling, and let's dig a little deeper into that. So how do we implement horizontal scaling? The simplest way to do that is resource-based, and the simplest way to do that is to use the built-in horizontal pod autoscaler that scales based on resource utilization. So this means that we would scale based on the CPU and RAM usage of a pod or deployment. So we will set a 80% CPU usage. Anything above that, we want to scale up. Same thing with RAM. We can say a percentage of RAM, after which we want to scale our pods from one pod to two pods and so on and so forth. We can also define a cooldown period for workloads whose metrics fluctuate in order to prevent flapping. If you have a deployment that is having a very varied workload and it's spiking, it's getting high requests and then low requests, we don't want to constantly bring up and down new pods. So what a cooldown can do is it will say, we will keep this pod running for a determined amount of time that's defined by the operator, and only after then will we bring it down. So that prevents that flapping of it coming up and down. We can also use the built-in HPA to scale based on custom metrics, but that's a little bit beyond the scope of this talk. But fear not, because we'll have a tool at our disposal that can help us scale on many other metrics. I'd like to introduce KEDA. KEDA is a CNCF incubating project that allows us to scale on one of more than 50 built-in scalers. These include Kafka, SQS, RabbitMQ, to name a few. There's also a lot of products from AWS, GCP, and Azure. It can also do resource-based scaling similar to the native HPA. KEDA uses a CRD, or custom resource definition, called scaled object that allows us to define how we want our scaling to happen. And we'll see this in action in a little bit. So now we've had a look at a little bit of a bit deeper look at how our horizontal scaling works. Let's now look at pod resources, node capacity, and why a pod would actually become unschedulable. That means that it's not able to run on a node. So we have over here a pod, and it has its resources. And in the resources, it has a request of 8 gigabytes of RAM. What does this mean? This means that when Kubernetes schedules this pod to a node, it guarantees that it will have access to 8 gigabytes of RAM. If we look over here, we see our node, it's got 8 cores CPU and 16 gigs of RAM. That's plenty for our pod to run, and it's running happily. Now, let's say that we want to deploy a new microservice, and this microservice has 12 gigabytes of RAM defined in its requests. We can see there's not enough space for Kubernetes. It doesn't have the resources on this node to schedule it, so that it's not scheduled, and now we have an unschedulable pod. So now we've seen how can we come to a situation where a pod is not schedulable? How do we fix this? That takes place with cluster autoscaling. So in order to schedule our pod, we need to scale the nodes in our cluster, which is called cluster autoscaling. We could do this manually, but that would be time consuming and tedious, and in DevOps we'll have to automate whatever we can. So the most efficient way to automate this is with cluster autoscaling. And so let's get an overview of how this works. It has two main jobs, which are provisioning or scheduling of new nodes and deprovisioning of existing nodes. The two most popular autoscalers are the native Kubernetes Autoscaler and Carpenter, which is an open source project developed by AWS. It only supports Kubernetes on AWS for the moment, but I believe that work is in progress to allow it to support other environments as well. So when you schedule new nodes, when does that happen? So that will occur when we have any unschedulable pods in our cluster, like the microservice we just talked about. It's waiting for its 12 gigabytes of RAM, it doesn't have it, so it's waiting for a node that can schedule it. The autoscaler will provision new nodes based on the requirements of unscheduled pods to ensure that we don't have any pods that are not running. That's the scheduling of nodes. Now, on the opposite side, we need to deprovision existing nodes. This will happen when we have empty nodes which are no longer needed as their workloads have been terminated. Let's say we have a scale up or scale out event and a new pod has been deployed. It's finished its job. Kubernetes has terminated it, but now we have that underlying node, those underlying resources sitting and doing nothing, and we're paying for that. So what the autoscaler will do is it will actually deprovision those nodes, so we're not paying for compute capacity that we're not using. Consolidation is another reason why we could have deprovisioning, and this is a unique feature to Carpenter. What it will do is it will look for ways to optimize how your workloads are running and consolidate them onto fewer and cheaper nodes where possible, and that can be a great source of cost savings. Another reason why it could deprovision nodes is based on events or interruptions, such as spot events from AWS, health events, or also custom events that you set up. So that's a brief overview of how cluster autoscaling works. Let's now wrap it all together. By combining these two concepts of horizontal and cluster autoscaling, we can achieve what we're terming Kubernetes elasticity. This allows us to dynamically scale up and down our cluster to meet constantly changing load on our systems. By doing so, we are able to achieve our goal of this session, which is to provide the best possible experience at the lowest possible price. So we can scale up both our nodes and our workloads as we have more increased demand, and we can scale them down in times where the demand is less. So now let's see how all of this actually works in action. So we're going to have a little demo over here. And what I'll be showing in this demo is the Kida scaler for the deployments and pods and Carpenter for the nodes. This demo will be focusing on an AWS-based ecosystem, but most of the techniques and methods used can be translated in some form or another to other environments. So first, let's take a look over here at our infrastructure. We have an EKS cluster on an EKS cluster running on AWS. We've got our SQS queue where we're going to produce messages to, which are going to be consumed by our consumer application running inside of Kubernetes. And we'll start over here on the side with the consumer resources. It's important when you're doing scaling that you define your limits and resources that your applications need in order to be able to scale efficiently, so that Kubernetes knows when it's reaching its limits, how much RAM and CPU it needs, and so on and so forth. So in this example, we've given each pod 1 GB of RAM and 750 millicores of CPU. Then we have over here our CRD, our Kida CRD, which is the scaled object. And what this defines is how Kida is going to scale our consumer deployment based on the definitions that we've given here. So we can see over there that it's going to scale based on the consumer deployment. And we have a polling interval of 2. What this means is that Kida will check the SQS queue every 2 seconds to see how many messages are in the SQS queue. And based on that, it will decide whether or not it needs to scale up. Obviously, that can be changed for the purpose of this demo. It's quite low so that we don't have to wait too long. Then we have a min replica count and we have a max replica count. What these mean is this is the minimum amount of pods and the maximum amount of pods that Kida will scale. And it's interesting to note over here, because we are dealing with the consumer, it's not responding to a request such as an API server. If there are no messages to consume, we don't actually need to have any consumers running. So we don't have to waste any resources running something that's essentially sitting idle. And then for the purposes of this demo, we are scaling up to a maximum of 5. But again, you can increase that depending on your workload and performance of your application. Then dropping a little bit down, we have our queue URL. That's the queue that Kida is going to poll, that we're going to consume our messages from. That's the name of the queue in my demo over here. And then we have the queue length. What this tells Kida is in increments of how much will it scale. So for every 5 messages in the queue, Kida is going to scale up by 1. So if there's 5 messages, it will deploy 1 pod. If there's 10, it will deploy 2, and so on and so forth. And finally, the last piece of configuration is the Carpenter provisioner. What this is what defines the nodes that Carpenter will provision, and there's a plethora of options. I've kept it simple for this demo, but I highly recommend to read the documentation. It's really powerful and it can do a lot. And the 2 things that we'll focus on over here is we've got our capacity type, which we've set to spot, which will allow us to save costs by only deploying spot instances. And the other one is the instance category, which we've set to T-type instances. Again, this is highly configurable, and depending on your requirements and needs, this can be highly configurable. So now I'm going to switch over to my terminal. If you'll just give me 1 second, and we'll see it in action. Okay, so if you can see my terminals over here, I will do a quick list of all my pods in my cluster. And as you can see here, we've got Carpenter running, we've got Kida running, and then a bunch of system applications which aren't really relevant for this demo. And then another thing to note over here, in the default namespace, we have no pods running. So we have none of our consumers are running. What I'm going to do now is I'm going to start my consumer, which will just produce a bunch of messages to our SQS queue. Okay, now that we've done that, what I will show you is in AWS, sometimes it takes a couple of seconds to reflect, but let's see. Let's just run that. I want to wait a couple of seconds. Sometimes it's not instantaneous. There we go. We can see now we've got an approximate number of messages. There's messages in our queue. So what we're going to do now is we are going to watch our default node space. And we can already see that Kida has brought up consumers. Remember, there were none there before, and there are now. And over here, I'm going to watch for my nodes. And as you can see over here, sorry, Carpenter, has already started bringing up a second node. So you can see this node is older. It's running the core applications. It's been running for 7 days. This is a new node, and it's come up and it's provisioning in order to run our new consumers. So it's not instantaneous. It can take up to 5 minutes. Normally it's quicker, but you'll see now that the node is ready. And we just have to wait a little bit in order for the containers to go from container creating to running, and then it will finish running the queue. So we just have to be a little bit patient. It's 30 seconds or so, but it will happen. So there we can see all our pods are running. And if I check the logs of my application over here, we'll be able to see all the messages being consumed. And that's a bit quick, but you can see the different IDs of the pods. And in the message, I'm just using some lorem ipsum messages as my consumer messages, but it's going to consume all those messages. And once it's finished consuming all those messages, as you can see here, those are the final messages that have all been received. And now Kida has terminated all our consumers because they are no longer needed. And Carpenter has already disabled scheduling on our node because it's also not needed. And if we just check one more time over here for pods, we should see that there are no pods in our default namespace. All 5 of those pods have been deprovisioned. And again, over here, if I check my nodes, you will see that we only have that single node. The other node has been brought up. It's done its work and it's been brought down, so you're not paying for the compute. I hope that demo made sense and was enlightening on how autoscaling works in practice. And now over to Ellie, who's going to tell you and show you how you can optimize and put everything that we've done here. You can optimize that in a much better way. Thank you very much.
So, hello everyone. My name is Eli Birger. David, thank you very much for the presentation. Lovely. So I'm a CTO of PerfectScale, and what we do in PerfectScale, we are focusing on the day 2 operation done right, or practically right now it's Kubernetes optimization and governance. Why we are dealing with this situation? So as in the example that you just saw, we have a dynamic system which reacts to different conditions, and it's extremely hard using the current. It's extremely hard to ensure that our systems are properly configured and tuned. Let's talk a little bit about the scope of the problem in a few seconds. So every time we assuming that something may be not properly optimized, the optimization flow goes as this. We first of all need to find where the over or under provisioning, where the optimization is needed. Then we need to analyze and figure out how to optimize this particular area. Then we need to plan, execute, and there is additional step to come over later and see that we actually optimized everything and what is the impact of our optimization. But when we're talking about this colossal and ephemeral beast like Kubernetes, where all the parts are constantly moving, developers are making many deployments a day. We have multiple nodes, and we have cluster autoscaler that schedules nodes on and off. We have HPAs, triggers, different replicas. We have jobs. This pattern is not scalable. We cannot figure this out. Why is that? There is multiple reasons. The main reason, we have monitoring issue. We have monitoring solutions. We maybe have a FinOps solution, but they all provide us with data. Still, data is not the answer that we are looking for. And why it's not the answer, or where's the gap between those two? So first of all, the pets versus cattle. This is a well-known paradigm. This paradigm talks about when you have a single server, you can build a dashboard, and by single site of this dashboard, you can understand how your pet or your server behaves. But what happens if you have hundreds of servers and they are dynamically popping up and down? Then you have a cattle, and you need, and even if you build such a dashboard, you will not be able to understand anything in this dashboard. You need different tool to be able to observe the cattle and be able to detect the sick pet and then fix it. The second thing is prioritization. Which of the optimizations would bring the most impact? The third thing is collaboration. How do you, in many situations, okay, you observe the problem, but you are not the service owner. Now you need to collaborate with the service owner in order to adjust everything. And lastly, because of the ephemeral nature, because of constantly changing environment, because of constantly changing usage pattern of our customers, we need to be able to make this work as fast as possible. With that, I'm moving to the actual presentation or to the actual product. So what do we see right now is a cluster. This cluster contains 262 different workloads, deployments, stateful set, jobs, whatever things we have in our cluster. And we are looking right now at the aggregated and combined view of this cluster for 1 month. What do we see in this big picture of this cluster? We see that our P99 of utilization was 60 cores of CPU to 154 gig of memory. But as David explained previously, everything is tightly coupled to the requests of your particular pods. And in most of the cases, the requests definitions are done by developers, and in most of the cases, they don't do any load and performance testing to figure out what would be the right size of resources. Instead, they're guesstimating, and in many situations, so in this particular cluster, the overestimation, because we are not very good in guesstimating things, was 3 times more CPU, 2 times more memory. And this is where our cluster autoscaler or Carpenter reacted and scaled up resources nearly 7 times more than needed in this particular cluster in any moment in last 1 month. So we are very, very heavily over provisioned. We are overpaying like 6 or 7 times more. And we, as PerfectScale, we detected all these opportunities to save this money. However, we also detected 129 different places where you can, where the definitions were done wrongly and creating risks like out of memory, CPU throttling, evictions, and many others, despite the fact that entire cluster have all possible resources in place. So let's see how we can improve this situation. So first of all, let's focus on the waste. I will sort now all of my workloads by waste. And the first one that will pop up is this collector catcher. This is a deployment running in a namespace of prod. Based on how many replicas we had, and based on what type of nodes this replica actually ran off, how much those nodes are cost, is it a spot instances, on demand instances, etc., we can figure out how much we spent for a particular workload. And out of this $94, $85 were completely wasted. Let's see how. So this workload had somewhere between 1 to 5 replicas with average of 3 replicas during last 1 month. There is 2 containers in each pod, the Jaeger that collects the traces and the actual business logic container. And what we see is that each replica provisioned with 10 GB of memory, 2.5 cores of CPU. However, looking over 1 month of utilization of all those replicas together, what we see that in 95% of the time, the utilization is below 2 GB of memory. The highest spike across all the replicas, across 1 month of utilization, was 2.2 GB of memory. So we're basically wasting 8 GB of memory, multiplied by 5 replicas, multiplied by 1 month of utilization. There is a lot of resources that are wasted. So how do we optimize that? We PerfectScale calculates based on the seasonality waves of your load, based on the overall trend of utilization, spike anomalies, and many other things. We are calculating how much resources do you need in order to run this workload effectively. And then all those recommendations are here coming wrapped into the YAML file. So copy paste it into the infrastructure as a code, run CI/CD, and you fix the problem. As I mentioned, in many situations, we are not the actual owners of the service. We cannot make any changes, or we can just talk to a relevant person. So instead, we can create a task. This task will go directly to Jira and will contain all needed information about what exactly needs to be done with this workload. And by that, we hooked the problem into the standard workflow of our engineering department. They will fix it exactly as they fix any other bug or issue in a system. So the other side of the same coin is the resiliency issues. This is where we found those 129 different problems. So first of all, let's sort by the cost. In most of the cases, the most expensive workloads are the most important ones. And we have this Couchbase here. This Couchbase have a resilience issue. Let's see what the resilience issue with this Couchbase. So it's relatively simple. We see it clearly. There is a low CPU throttling. Why this throttling happens? Because someone at some point in time provisioned this Couchbase with 1,000 millicores as the request, 3,000 millicores as the limit. It might be correct at the moment it was set, but since then everything changed. We deployed a new microservice with heavier query, and now we need more CPU. We changed something in the type of data, we have more customers, we have just simply more data. We don't know exactly what is the reason, but in 95% of the time, we already need 2 cores of CPU. The highest spikes are very, very close to this limit, so that's the reason why we have the CPU throttling. Now, we can say, yes, but there is a monitoring or alerting solution that will help us and alert. Let's think about it for one more second. When those throttling will happen, it will happen on the highest spikes that we will have during the day. Those spikes by nature will be relatively short, so our alerting system will alert, and the alert will be self-resolved very fast, but it will still create a latency for our customers. So again, PerfectScale comes with recommendation how to fix this and all the rest of the problems together. Now, the next thing that I wanted to show is this, again, a cattle view. We're trying to go up and observe everything. So here is all of my clusters together. I can understand where they're running, in which region, what's the resilience level of them, how many risks they have, what's the waste, what's the cost, and even coming soon, a carbon footprint of those clusters. Because don't forget, at the end of the day, when you reducing the amount of resources or the cloud waste, you are not only saving money, you're also reducing the carbon footprint or the carbon impact of your clusters. And at the end of the day, we all live and share the same planet. So from here, we can actually jump to the view that you are guys already familiar with, is this state of cluster where we can see all the problems, etc., etc. We do have alerts, so we will alert you where every time there is a resilience issue, cost anomaly, or waste anomaly. And the last thing that I wanted to show for this demo is the trends. This is where we can evaluate how, for example, okay, so let's start here. For example, we are observing all of our clusters together. This is a very, very common situation. Our cost is growing, and we want to understand why. There is very, so let's focus on this particular cluster, which went from $423 to something like $1,600 within a month, and then reduced a little bit to $900. We want to understand what exactly happened here, and let's see. So we will select this cluster. We will switch to the view of workloads of this cluster. And we will observe these clusters in a day, this cluster workloads in a view of days. I will remove this title. So our cluster consists, sorry, it's the wrong one. Yeah, I prefer this one. Okay, so our cluster consists 72 plus 15, it's 87 different workloads, but 72 of them, the total combined impact is only $4 out of $40 per day. So we can completely, like, don't look at this area. And let's look at the most impactful ones. And we see that there was a workload which cost us $20 per day. And this workload removed from the cluster on 29th of March, so if we will look at the monitoring solutions, the FinOps solution, we will not find it there. However, it left his footprint on the cost. The other very expensive workload went from $2 on 20th of March. It increased in cost somewhere to $10, then decreased, increased again, and now it becomes stable. But on 7th of May, there is a new workload that heavily impacting our cluster right now. Let's see how the waste look in a similar view. So we had this waste. You remember the workload, the first one that we saw? Here is a waste, and this waste was reduced. It jumped again, and now it's slightly decaying. But the new workload was that we detected here, creating a very, very huge waste. So this is where the biggest opportunity to save right now. In the same view, we can also evaluate the risks. Who are the workload that creating most of the impact in terms of resilience of our cluster? With that, we can switch to the questions.
Yeah, thank you, Eli, and thank you, David, for this really interesting topics. We have a few questions. Feel free, everyone, if you want to submit some more right now. So the first one, I think it's for you, Eli. It's from Dor. And he's asking, how do I deploy PerfectScale to my cluster?
Yeah, that's a great question. So here is so PerfectScale is basically simple agent, stateless deployment that's running inside your cluster. How do you deploy it? You deploy it here via add cluster command. You create a name for your cluster. You create a secrets for your cluster and you run this helm command. That's it. That's all the installation. Within 2 minutes, you will have the visibility for everything that goes inside this cluster.
Okay, another question, I guess this is for you, David, from Alex. What event types can KEDA work with?
So there's a lot of them. I think at the time of this, now it's over 60, but some of them are, like I mentioned before, they're Kafka, RabbitMQ, a lot of AWS technologies such as SQS, SNS, things like that. We also have from Azure GCP as well, Redis, and can do a bunch of databases like Postgres, even ArangoDB. The list is very long. I mean, we could spend the whole day talking about them, but I highly recommend checking out the documentation. It's got it all there. And you can also write your own ones if there's something there that you don't have.
Great.
I want to add to that also another one very useful. It's a cron. For example, you can scale your environment in the morning and then scale down in the evening based on KEDA.
Great. Livan is asking, will there be a video available later? Yes, there will be a video. We've got another question regarding PerfectScale. Does PerfectScale work on OpenShift cluster? Do you have any operator to play around?
Yeah, so first of all, we are completely cluster agnostic. We are completely cloud vendor agnostic. So it will work on any cloud and any Kubernetes as long as it have the standard Kubernetes APIs. So vanilla, kops, CKS, GKE, OpenShift, whatever, we will support it all. Any cloud, I mean, also including your own data center. The only difference, when you're running it on a bare metal, you will need to configure the price for the CPU and memory or for a particular type of the nodes. All the rest of the calculation will work exactly the same. There is no operator. We're providing 30 days free trial. Contact us in order to be onboarded. The onboarding takes only 15 minutes, and it's just basically helping you to install the Helm command inside your first cluster. All the rest you do by your own.
Okay, so another question here. Is it possible to run HPA and VPA at the same time? For which one of you that wants to take this?
So I will take
answer. Go for it. Go for it.
Yeah. So the answer is no. The reason for it's not the only problem of VPA, but yes, this is one of the biggest ones. The reason is that VPA looks at every container separately. It have no idea that some of containers are replicas of the same entity. So eventually, imagine some situation like, let's say, you set a request to be 10 gig, and you are utilizing now 6 gig because you have 2 replicas and the load is equally spread. Then VPA will suggest you to reduce the amount of memory to be 6, and then HPA will trigger more replicas, and then VPA will recommend to reduce more, and this will be endless competition between those two tools.
Got it. Thanks. Irena is asking, does PerfectScale provide any alerting solutions or is it entirely manually monitoring?
Yes, so PerfectScale provides alerting solution. The alerting is covering, the alerting currently goes to Slack and within a few weeks to Teams. It alerts on the resiliency issues like out of memory, CPU throttling, evictions, node failures, frequent restarts, etc., everything related to the resources, as well as cost anomaly and waste anomaly. The one thing to add on the cost anomaly and waste anomaly, it's coming soon. The reason we're building here something a little bit more complex than it's in regular or competitive products. In most of the cases, to be alerted on the waste or to be alerted on expenses, you first need to spend those expenses. So, for example, if you have cost anomaly of $1,000, you will see the alert for this $1,000 only after you spend this $1,000. PerfectScale understands how the workload behaves, and based on this behavior, PerfectScale makes a prediction and can alert you way before you actually spend this money.
Okay, this one for you, David. When would you prefer Carpenter over Cluster Autoscaler?
So anytime that we're on AWS, I would prefer Carpenter. It's more tightly coupled, so you don't need to use autoscaling groups, so it reacts faster. Also, you can have multiple different types of the node instances, whereas autoscaling groups only work with a specific instance type. And it generally, I've found in my past experience, it provisions the nodes quicker, but obviously for now, it only supports AWS. So any other, if you're using GCP or Azure, you'd have to go with the cluster autoscaler.
Okay, we have a couple of more questions. This one's from Leven again. How about downtime while scaling?
Okay, so that I would say depends. It depends on your application. So if you have an application that's stateless and like I mentioned, a REST API consumer where you're bringing up, let's say you've got multiple instances of your application. So then what Kubernetes will do based on a pod disruption budget, you can actually define how many pods you need running at a specific time. That's configurable by yourself. You can have a maximum amount unavailable, a minimum amount available. So depending on that configuration, Kubernetes will ensure that you have uptime of your application while it's actually doing that rollover of that scaling. So that, yes, for most things, you will have maintain uptime.
Great. Eli, this is to you. How do you calculate the price? There are a lot of dependencies.
Yeah, so basically we're following the pattern of each and every pod or each and every container, if you will, within a cluster. We understand, we're measuring every 30 seconds, we understand where you're running, which pods are running, on top of what nodes they are running, what fraction of each node is allocated for each and every pod, what type of instance is the particular node, what type of reservation it is, and which region it is. So by that, we are capable to understand, by combining all these fractions together, to understand the particular cost.
Okay, got it. Thanks. And last one for you, Eli. When do you recommend, or I'll rephrase what is written here, for what size of company do you recommend to use PerfectScale? Is it like just for small companies, or is it for bigger companies also? Is it just for big companies, or is it for small companies also?
Yeah, so obviously as the footprint of your Kubernetes environment grows, the benefit will be bigger. The first thing like when you're getting to the size of, let's say, 3 clusters with 20, 30 different workloads in it, it becomes humanly impossible to use monitoring solutions to understand what's going on in this cluster. So that's really the breaking point from not having PerfectScale to having PerfectScale. Said that, we have a free offer up to $10,000 compute of your Kubernetes. You can use PerfectScale for completely free.
Great. Thanks, Eli. And now we have a question from Tural here. Is there any way to instruct EKS Autoscaler to shut down the instance, not to terminate it during scaling time, so we can use warm pull function of autoscaling groups.
So with Carpenter, for example, I'm not actually sure with cluster autoscaler, so I can't answer that. But I know with Carpenter, for example, it doesn't actually work with autoscaling groups, so it won't work with that, because I think it can do warmer nodes, but it doesn't use autoscaling groups. It's done via a different mechanism.
Yeah, so I would like to add on top of that. So basically, what you're trying to do is to keep your cluster be capable to hold the load of coming situation. Your load have normally kind of seasonality, and you want to add some kind of buffer on top of that. You cannot rely on speed of bringing nodes in. It could take somewhere between half minute to 5 minutes to bring the node. And then this node need to download the image. And in many situations, your image by mistake could be not multi-stage image, but a huge one. And then you starting the pod, okay? You basically starting the process, but it may have the ETL inside. So it need to bring some data from some database, it need to build up the cache, it need to send the health checks, etc., etc. So the amount of time that you will have from the moment that you need the pod to the moment that this pod is available is completely unpredictable. And the only way to treat that is to make sure that you have enough capacity at any given moment.
Thank you. So I guess no more questions here. I'd like to thank you both and to thank everyone that joined us and sat in on this talk. It was very interesting. And as I said, a video recording of this talk will be available for all those who signed in and registered. And thanks guys, and thank you everyone for joining.
Thank you.
Bye-bye, everyone.
Bye.
Bye-bye.